We're continuing with this section on the thermodynamic aspects of phase transitions. The last lecture we talked about the changes in the chemical potentials of the phases caused by changes in temperature or pressure. In this chapter, in this little section, we'll be looking more at the shapes of the phase boundaries, things like their slopes. So we're looking at the slopes of those lines in the phase diagrams. And to do this, we take into account the fact that what we're looking at here are coexistence curves. Every place along these curves, the two phases, whether they be solid and liquid or alpha, beta, whatever you want to call them, they have the same chemical potential at that phase boundary. So if they have the same chemical potential at A here, they're going to have the same chemical potential at B. So there's going to be, and this is some change in pressure and some change in temperature, but the chemical potential is not going to change. Or rather, the chemical potential is going to change, but it's going to change the same amount for both phases, right? Because they have to be equal here and here. That's how we're going to do this derivation. So the change in the chemical potential of each phase must be equal, right? As we change the pressure and the temperature. So now the change in the chemical potential, which we saw from earlier, was equal to the molar volume times small change in pressure minus the molar entropy times the change in temperature. So then do this on both sides. We say that for the alpha phase, the molar volume of the alpha and the entropy of the alpha on one side, and the molar volume of the beta and the for the beta phase and the entropy of the beta phase, and then you collect terms and you end up with the slope that we're looking for, the change in pressure with the temperature along that line, whatever that line is the change in the molar entropy, all right, between the two phases, and the change in the volume, molar volume between the two phases. Okay, now we give these a name. We're going to call these the delta transition of entropy, right, or the delta transition of volume. So it's the molar, each one of these terms is the molar entropy of the products minus the reactor, whether they be B minus A, beta minus alpha, and the change in the molar volume of beta minus alpha. This whole thing here is called the Clapeyron equation. Okay, Clapeyron equation. And sometimes we want to do the opposite and just take the reciprocal. So instead of dP over dT, you just do the opposite, dt over dP, and you just flip things here. So this can give us, because we're sometimes looking at how much it goes in reverse. Okay. Remember, this up here was what we called the fundamental equation of chemical thermodynamics. And this Clapeyron equation here applies to any coexistence curve for a pure substance, right? It only gives the slopes at a point, right? So as the entropy changes with temperature or pressure, and the volume changes, then this changes. But at slope, at that particular temperature and pressure is given by this form here. There's no other approximations here. Okay, but now we do want to make an approximation. This is just a mathematical thing. You may have seen this in calculus or in algebra. If you have a natural log of 1 plus x, right, you can write an infinite series, right, that especially for small x, you can approximate that as x minus an x squared term, an x cubed term, and so forth, a large number of terms. But now if the x squared term, if this term is much less than the first term, right? So if, for instance, if x was equal to 0.1, then 0.1 squared is 0.01, so x squared is much less than x, right? So for x is about 0.1, so if it went from 1 to 1.1, right, so the natural log of 1.1 is approximately 0.1, right? That's what this says. Okay, so now if you have 1 plus x, all right, if that's approximately the x. Now, if you have instead, what we're going to do is we're going to have an x is equal to an x naught plus a small change. Right? This could be the temperature plus a small change in temperature of a volume plus a small change in volume. Right? So we have x equal to x per plus, and this delta x is much smaller than actually it should be x0. Right? So we're a small change in x. Right? Now, if you take the natural log of x over x0, or natural log of the new volume over the old volume, right? Something like that, right? Now this x is equal to x0 plus delta x, right? So then we can take, this becomes 1 plus delta x over x0, so the natural log of it, and this whole thing then using this approximation, 1, since delta x is much smaller than x0, then the natural log of x over x0 is approximately delta x over x0, right? Where delta x was the change. So we're going to use this approximation in this next calculation. This slide, we're going to focus on the solid-liquid coexistence curve, right? Just the boundary between the solid and the liquid. So since you're at the boundary there, this is the melting point or fusion point, right? The entropy change of fusion there is the enthalpy divided by the temperature of that at that boundary. So we're going to make then modify the Clausius-Clapeyron or the Clapeyron equation by, instead of using delta S, we're going to use delta H over T. So now this slope, delta P over delta T, is delta H over T delta V, right? And we're going to assume that these enthalpy changes and volume changes are constant over the where we want to find the slope, right? So they're not changing very much. Then you just have to integrate this, right? You take this and you separate, you put the dP on one side, right? You integrate the pressure there. On the other side, you have the temperature, and since we're considering these as constant, you pull these out of the integral, the enthalpy and the volume changes, you pull them out. So now you're just integrating on the left side delta P, because it's P2 minus P1, and on the other side, it's the integral of 1 over T is going to be the natural log of T2 over T1. And then what we just saw in the last approximation, that we can approximate the natural log of T2 over T1 as delta T, right? If it's a small change in temperature, right? That's what we had done in the previous slide. So what you end up with is delta P is equal to delta H, or this slope, delta P over delta T, is delta H over T delta V, which looks an awful lot like this. What we've done is change these D into deltas, but you can understand that the approximation we made, because we actually did the integrals, only holds for small changes, or the small change in temperature. So if you're going from 300 to 320, that's fine. But if you're going to 300 to 500, that's a lot, right? So it has to be small change. So this is then the slope that we're looking at here. The slope for the solid liquid, right? And we're saying that it's delta H over delta V divided by T. Okay. So let's calculate the temperature that water freezes at 15 bar, right? Rather than 1 bar. What is it at high pressure? Okay. So at normal temperatures, 1 bar, it freezes at 0 degrees Celsius. And the enthalpy of fusion is 6 kilojoules per mole, which you get from calorimetry just by seeing how much heat it takes to melt ice, right? And the volume of fusion, the difference between the density for 1 mole, or the inverse of the density of 1 mole of ice versus water, is negative 1.6 centimeters cubed per mole, because the ice is um, um, less dense than the water. All right, so now we start with this equation that Clapeyron delta P over delta T is delta H over V. We plug in the delta H value, 6 kilojoules per mole, all right, and then you plug in the delta V, which is the negative 1.6 times 10 to the minus 6. You had to turn this into meters cubed, okay? Of course, you have to turn this 6 into 6 times 10 to the 3 joules, right? And then you do that calculation, you end up with negative 1.4 times 10 to the 7th, and then the units are going to be Pascal per Kelvin, okay? Which you can then turn into bar, which would end up being negative 140 bar per Kelvin. And now if we want to change by from 15 bar to 1 bar, that's a change of 14 bar, because we've increased the pressure by 14 bar, and you divide that by negative 140 bar per Kelvin, right? You end up with, when you increase the pressure by 14 bar, the temperature drops by 0.1 Kelvin. So instead of being at 0 Celsius, it's negative 0.1 Celsius. So that would be then the boiling point at that higher pressure, or melting point at that higher pressure. So we looked at the slope of the solid liquid coexistence curve. Now let's look at the slope of the liquid vapor coexistence curve. So we use the same equation. dP dt is delta H of vaporization over T. Well, actually, it's a different equation. We're using the delta H version, the enthalpy version, times temperature, but over the change in volume. But now the change in enthalpy for vaporization from a liquid, is more than that it is for a solid to a liquid. But, just by, factors of 3 or something like that, not at large numbers. But the change in the denominator here, the change in the volume when you go from a liquid to a gas is so much greater than it is when you go from a solid to a liquid. Because of that, the slope at the where they come together is much closer to the same. So we're looking at this curve here. We're looking, say, at the triple point. You can see the slope here is much less than the slope for the solid liquid. Solid liquid slope here is much steeper than it is for the liquid gas. Okay, that just comes because the change in volume is so much larger. Right, the change in volume is so much larger. Let's look at an example of just estimating the slope here. So we're going to use Troughton's rule that we talked about for the delta S being about the same for a wide variety of materials, and we're going to estimate the effect of changing the pressure by 0.1 atmosphere on the boiling point of any liquid, or any liquid that's similar to following Troughton's rule. Okay, so that ratio, delta P over delta T, we said could also be written as delta S over delta V. Okay, so using Troughton's rule, and also assuming that the change in the molar volume of the gas, going from a liquid to a gas, it's mostly just the gas, right? The liquid has a very small molar volume compared to the gas. So we're just going to replace it by RT over P, all right? Treat it as an ideal gas, right? So then this delta V is going to be P over RT here, RT over P, right? And the delta S we're saying is around 85 joules per mole Kelvin, because a lot of materials are close to 85 joules per mole Kelvin. So we have 85 joules per mole Kelvin. The pressure, we're doing this at 1 atmosphere, so it's 10 to the 5th pascals. And then we put in R and T. This is, this was something that was boiling at room temperature, I guess. All right. And you end up with, or near room temperature, with 3.4 times 10 to the 3rd Pascal per Kelvin. which means that if you increase the pressure by 0.1 atmospheres, which would be 10 to the fourth, right, Pascal, the boiling point would go up 3.4 Kelvin. So this is just an estimate for a lot of materials that follow Troughton's rule. And in fact, you can do this for water. Water doesn't follow Troughton's rule. We said it's an exception, but it's on the same order. It comes out about the same. So a 0.1 atmosphere change would be changing the boiling point of water, although in this case, So we can use an example of this. If you have been to Mammoth Lakes, California, a ski resort in California where you can go and ski in the winter or go hiking in the summer, it's located at around 8,000 feet. We used to go there frequently. And 8,000 feet, you don't have 1 atmosphere of pressure like you do here in Ventura County, because you're not at sea level anymore. And the pressure there is about 3/4 of an atmospheres, so 0.75 atmospheres. So using this estimation here, when you drop the pressure by 0.25 atmospheres, it's going to drop around, it turns out the boiling point is 93 Celsius. So it's 7 Celsius less than the 100 Celsius is, which is why it takes longer to cook your spaghetti or your ramen noodles when you're visiting Mammoth Lakes, because the temperature is not as hot in that boiling water. Okay, we're now going to look at the further at the shape of the liquid gas line, right? The boundary between liquid and gas. And we're going to use this same approximation that we just did, that the volume change is mostly just the new volume of the gas. We're ignoring the initial volume of the liquid. So as we did before, dP over dt is, in this case, we're using the enthalpy change, enthalpy over T, and we're using the RT over P here. Oh, that's a little p. Okay, and we'll rearrange that, put the P in the numerator. So now we have dP over dt is the pressure times the enthalpy change over R, and now we have T squared, right? RT squared, okay? And now you move things around. You end up here with dP over P on the left side, because I moved the P over to the left side, and leave the dt there, and we bring all the constants over to the right side, right? And now the natural log of P, dP, if you take the natural log of P, the derivative, of natural log of P is 1 over P, right? When you integrate 1 over P, you get natural log of P. You take the derivative of natural log of P, you get 1 over P. So instead of dP over P, instead of dP over P, we're going to use d natural log of P, right? So you end up with the d natural log of P dt, that's what we have over on the left side here, is equal to delta H over RT squared. So this is only for the case of gases, well, actually, anything going to a gas, whether it's a solid going to a gas or a liquid going to a gas, where you're ignoring the molar volume of the solid or the liquid that you started with. So you end up with a delta H of vaporization in the case of liquid divided by RT squared is equal to this. This has its own name. It started with the Clapeyron equation, but because of this, in this specific case, it's now called the Clausius-Clapeyron equation, right? The Clapeyron equation was kind of universal. The Clausius-Clapeyron equation is ignoring the volume of the liquid that we started from. So now let's look at the vapor pressure versus temperature, which is essentially following that curve, right? So with temperature, see what happens with pressure versus temperature. We're using this Clausius-Clapeyron equation, and so we're going to put the d natural log of p over on the left side, and we'll have the dt on the right side. And you can move this out of the integral because these are not changing with temperature. We're assuming they're not changing with temperature. For delta H of vaporization, it does change with temperature, but for it's a pretty small change compared to the other things they're going to be changing. And then the d natural log of p, right? So when you integrate the d natural log of p, you get the natural log, since it's just like dx, you get x at p2 divided by x at p1. Well, this case, it's the natural log of p2 over natural log of p1. On the left side, here you have the delta H over R, and then the integral of 1 over t squared, right, is going to be 1 over t. So you end up with 1 over t2 minus 1 over t1, and then the negative sign out here in front. Okay, which came because when you integrate 1 over t squared. Right, and this whole thing here can be rewritten. Instead of natural log, you take e to both sides, right, and you move the p over here. It ends up being what we change this now to the vapor pressure, and then this is vapor pressure at standard conditions. We use this p star, the standard conditions. So p is equal to p car standard conditions times this factor. It's an exponential, which has delta H in it, and it's 1 over t, right? So you can see now, from this Clausius-Clapeyron equation, you can get if you take the natural log of p, first of all, versus 1 over t, going back to this earlier one here, if you plot the natural log of p versus 1 over t, so the natural log of p versus 1 over t, right, from an experiment, you'll extract the slope as being this negative delta, the enthalpy change divided by R. And that's actually the crux of one of the experiments that you do in Lab 372, where you boil something at different pressures and find out its vapor pressure to find the enthalpy of vaporization. And that comes from the Clausius-Clapeyron equation. And it gives us the shape of this curve here. Now, I should point out that most of the time you look at these curves, they're not necessarily linear. This one is linear. I went to the trouble of finding a linear curve. This is for carbon dioxide. And you can see the shape of the pressure here is going up exponentially. It's exponential. You can see it's P is equal to whatever it was at the triple point times e to the minus delta, this whole thing here, and then it's 1 over t. So it's not with t, it's with 1 over t. But anyway, it ends up looks kind of exponential. But it's really, you take the natural log of pressure versus 1 over t, it would be a straight line. And now you can also look at the solid vapor coexistence curve down here, and it's also going to look kind of exponential because of the same reasons. It's going to follow that Clausius-Clapeyron equation. But if you look at where they come together at the triple point, all right, since the delta H of vaporization, sublimation, going over this curve here, remember, is going to be equal to the delta H of fusion plus the delta H of vaporization. It's larger, and because that delta H is in the denominator, this slope here, it's in the numerator or denominator? It's in the numerator, right? So if you take the natural log versus 1 over t, it's in the numerator. So the larger slope gives you a larger slope here. So you can look at the slope as you're coming into the triple point for the solid is greater than the slope for the liquid part, right? They're equal, the values are equal here, but the slopes are different. That's just because the delta H's are different. The delta H of the vaporization is smaller than the delta H of the sublimation.